In this lecture, we'll look at the existential in and the quantifier exchange rules for our predicate logic proofs. Looking at the rules, so we've already done our existential out and our universal quantifier out rules here before. So we're just adding this existential in rule and then our quantifier exchange rules down here. So the existential in rule is pretty straightforward. The whole idea is that if you have something that has a constant fixed to it, then you can say that something exists. So from a statement in which you have a particular term with a particular constant, you can just replace that constant with a variable and then attach an existential quantifier to the front of it. The quantifier exchange rules are a little bit more complicated, I guess I could say, but they're sort of the same in reverse, so that's why you have 4 of them here. These two are the same, just going in different directions, and then these two over here are the same, just going in different directions. What I mean by that is from a tilde universally quantified statement, you can get an existential statement where you move the tilde in one place, and then if you have this, which is the same right here, you can just move the tilde out to the front and switch the quantifier over. So that's the whole idea of the quantifier exchange. That's where it gets its name from, is the fact that we're just exchanging the negation and I guess I should say we're exchanging the quantifiers as we move the negation from the outside to the inside of our quantifiers. In this lecture, what we'll do is we'll look at the existential in rules first, and then we'll do the quantifier exchange rules afterwards, and we'll also break it down into one-place predicates here in this first bit, and then we'll do two-place predicates afterwards. All right, looking at this first proof, it's pretty simple. It's only 4 lines long. So if we look at what we have as assumptions, we have a conditional statement, not an existentially quantified statement. Remember that if the existential quantifier was the main operator, there would be a set of parentheses saying that the scope of the quantifier goes to the whole statement, and this B would also be replaced by an X, but that's beside the point. So this is a conditional statement. Then we have just a regular term with a particular constant, and the same thing with our conclusion. So how do we get to our conclusion here? Well, it's attached to this conditional statement, so we just really need the left side of this arrow. From 2, what we can do is we can introduce an existential quantifier by replacing the a constant with an x variable. We get the left side of our arrow up here. So that's all we have to do. Because there's something that is a p, that means there exists something that is p. That's the whole idea. So we just add an existential quantifier to this statement up here, and then we can get the consequent, this QB out from our first line by doing 1 and 3 arrow out, and then that's it. Now this proof looks very similar to the previous one, and that's on purpose. I just want to show you again what's happening here. So we've got a conditional statement just like we did in the previous proof, and then we have something that is P. So we can build the left side of this arrow by doing our existential in rule, and then we'll have a universal quantifier, and we can just get whatever we want. So let's just add an existential quantifier to this line 2. And then once we get that, we have the left side of our arrow. We can get the right side, right? From 1 and 3 arrow out. And then I'm looking for QB, so all I have to do is use my universal quantifier out rule to get a QB derived from that, and then we're done. And pause the video if you think you want to try this one on your own. Okay, looking at what we have here, we've got a universal quantified statement here at the beginning. We also have a conditional statement here as a conclusion. So as with propositional logic, what did we do whenever our conclusion was a conditional statement? We assumed the left side, the antecedent, as a PA, and then we tried to get the consequent derived within our proof, and then we did arrow in. So guess what? Same thing we're doing here. We're going to assume the left side of the arrow as a PA, and then we're going to try to derive the right side here. So looking at what I have in 1 and 2, one of these is a universal quantifier, one of them is an existential quantifier. So which one do we have to do first? Hopefully you said existential quantifier because the existential quantifier is limited and the universal one is not. So we need to pick a constant to replace the x in our existential quantifier that does not appear anywhere in the proof. Luckily, no constants appear in the proof at all up to this point, so I'll just pick an a to place in this one place predicate by doing my existential out rule. Now I want to match this statement to what I have here, so I'm going to do a universal quantifier out on this first conditional statement up here. I'm just going to pick an a for the variable x to get them to match. Now I have a conditional statement. I have the left side of that arrow, so I can get the right side. So I'll pull out this QA from 3 and 4, arrow out. And then once I've done that, I have something that exists that is a Q, so I can just introduce an existential quantifier there. I'll replace the A with an X, fix the existential quantifier out to the front of it, and now look, I assume the left side of my arrow here in 2, I derive the right side of my arrow here in 6, so I can just build my arrow in line 7 from 2 and 6 arrow in, and then making sure that I drop out the assumption number associated with the PA here. Go ahead and pause the video if you want to try this on your own. So looking at what we have here, we've got an existential quantifier that's going to be restricted. We've got a universal quantifier and the other assumption that's unrestricted. And I've got an existential quantifier here in the conclusion. So might be a little concerned that we have multiple existential quantifiers in our argument, but the nice thing is that now that we have existential in, maybe we could just try to build this here with a constant in the places of the x. We have to make sure that the constant is the same when we go to replace it. But if we can build something that is q, p, and r, then we can just do our existential in all at once to build this statement. So that's okay. I think we're good. We don't need a PA here. We just need to try to get something that's q, p, and r pieced together in the right order. So based on what we've got, line 1, we've got an existential quantifier. Line 2, we've got a universal quantifier. Got to do the existential quantifier first. It's always limited. Always have to do it first. So I'll put it in A for all the x variables there. Then I'm just going to go ahead and break apart this conjunction here in 3. So that's what I'm doing here in 4 and 5. I'm just taking this PA, this QA, separating them out. And then we've broken down that first assumption to its simplest parts. So let's look at the second assumption, which has this universal quantifier attached to it. So to make it worthwhile, I'm going to replace the x's with a's, like I'm doing here. And now I've got this conditional statement. I've got the left side of this conditional statement. So in line 7, I should be able to get the consequent. So RA from 4 and 6. From 5 and 6, not 4 and 6. And then now I've got RA, and looking at what I need, well, I need to piece together this whole statement up here. And I do have something that is Q, something that's P, and something that's R. They're all A in this situation. So I got PA, QA, and RA. So I just need to piece them all together in the correct order. I need to piece together this first, and then I'll attach the R later. So I'll put QA and PA together here in line 8 with 4 and 5. And then after that, I can put the RA in on that. And now look, that matches this over here. I just need to use my existential in rule to build the statement that's in the conclusion. So everywhere that there's an A, the X gets placed. That's the key thing here. If these were different letters, if this was a B and this was an A and this was a C, whenever I did my existential in rule, I would have to, well, actually, I wouldn't be able to do it at that point. I'd have to do it up earlier. But the whole idea here is that the constant picks out the same individual. And so we're trying to say that there exists something that's P, Q, and R. And if the same constant is not in the one place predicates, then we can't say that there exists something that is all three at the same time. We can only say that there's something of each that exists. Hopefully that makes sense. That was a little bit more confusing at the end, but the important thing is that the constants have to match if you're going to use the existential in rule. Okay, go ahead and pause the video if you want to try this one on your own. If you did this one on your own, I congratulate you because this one is a little tough. So looking at what we have here, we have a wedge statement, so that should be setting off alarm bells that you're having to do wedge out. Then we have this double arrow, right? Because this existential quantifier only goes to the P and this one only goes to the Q. And we're trying to build these two conjuncts, so we just really need to get something that is a Q, and then we can do existential in, and the same thing, if we get something that's a P, we can do existential in. And so what we're going to do is we're going to have to start with a PA of the left side of our disjunction here. So remember with our wedge out rule, we need to assume each side of the disjunction as a PA and then derive the conclusion with both of the disjuncts. So that's what we're going to do. So if we assume PB as a PA, the next thing we probably want to do is we want to get this double arrow out. So that's what we're going to do here in line 4, is we're going to use our double arrow out rule on our line 1. Then we can add an existential quantifier to line 3 because we've got something that's a P, so we're just going to replace our PB with a PX. So that's what we're going to do with our existential quantifier in rule. The next thing is that we get out our consequent of this conditional statement from 4 and 5 arrow out. And look, we've got both of our pieces that we need to build our conclusion. So that's what we're going to do here in line 7. We're going to piece them together in the correct order. And then we can build our arrow. We assume the left side of our disjunction up here, we got to our consequent that we were looking for. So we can do 3 and 7 arrow in. We're all good there. Next thing we got to do is we got to assume the other disjunct as a PA and build the same statement again. So that's what we're going to do, and this is going to look the exact same as before. So we've got QC, and then what we want to do is now we want to use our biconditional out rule to get the other direction of the arrow here. We've got something that's a Q, so we'll just add an existential quantifier to it, just like before. And then we've got EXQX, so we can get EXPX here in line 12 from doing our arrow out rule. And then we just have to build our consequent like we did before, so that's what we're going to do here in 13, piecing these two together. And then now we've got the consequent that we was looking for, and then we've got a PA that depends upon it, so we can just use our arrow in rule to build the conditional statement that we need. Now we have our wedge statement here in line 2. We have one arrow statement here in line 8. We have the other arrow statement here in line 14. So we can wedge out to get our conclusion there in line 15. So yes, very complicated because of the wedge out rule, but hopefully you could see that lines 9 through 14 and lines 3 through 8 are the same exact rules, just getting repeated. So it was just about doing the same thing twice over. Now we're going to move on to two-place predicates for our existential in rule. So we'll just do like 3 of these, and then we'll move on to the quantifier exchange rule. Two-place predicates work the exact way as one-place predicates. It's just we have to be careful about the order in which we introduce our quantifiers. So if we look at this first argument, we have a conditional statement up here, right? This is our antecedent, this is our consequent, the arrow is the main operator here, so that's what is holding this statement together, and we're going to have to arrow out to get Q and R. Now we have something that is P, that it's a two-place predicate. So we can build this antecedent by introducing existential quantifiers. The only thing is we have to do them one at a time. So what we want to do is we want to add the Y one in first because it's the nearest to our predicate. And then we want to add the other quantifier, the EX one, last because it's the one that's furthest away from our predicate. So hopefully that makes sense. We have to build, I guess, inside out. Because order matters here. It has to be the exact same order to be able to match it up as our antecedent to our conditional statement there in line 1. So what we're going to do is we're going to add our existential quantifier here first, and since we need pxy, we need to make sure that the y is in the second position of the two-place predicate, and then we need to add the x second. So we're going to take this statement, and now we're going to remove the c and place an x in there for that existential quantifier. So here, just adding quantifiers to our assumption there in line 2, just in one at a time. So the key thing here is order matters. So we have to do whatever quantifier is nearest the predicate first and then move outward. So that's what we get here in line 4. Now we've got the antecedent to our conditional statement here in line 1, so we can get the Q and R from 1 and 4 arrow out, and then we just have to disassemble the Q and R and then reassemble them in the correct order, and then we're done. Go ahead and pause the video if you think that you want to try this one out on your own. Okay, looking at what we've got here. This is very similar to the previous one. Remember, we had a conditional statement. We had a quantified statement here as our antecedent. Then we had a consequent that already had constants in the different predicate positions here. So same thing as before. This time, though, it looks like we're going to have to do an existential in at the very end to build this. So what we should be going for is something that is S or R, and if we look at our assumptions, I see no R. I do have something that's an S, so what we should do is we should try to get this SC and then wedge in something that's R, namely it's going to have to be C, but I'll say a little bit more about that here in a second. So yeah, that's the idea here. We need to get to this S predicate because there is no R predicate in anything else that we've got here. So just like before, we want to build our existentially quantified p here. So we're going to have to do it one at a time. We're going to do the y first. We want to make sure that we put the y where the y matches up in the antecedent there. Same thing with the x. So now we're all good with that. We've got the antecedent to our conditional statement, so we can get the consequent of that, which is QA and SC. We can separate out the SC because, as I was saying before, we need to get something like this, and then we can add our existential quantifier at the end. With this now, this is a crucial move. What do we wedge in? We have to make sure that what we wedge in is RC so that the constants match. As I was saying before, we can't do an existential in if the constants do not match each other within the different terms. So we have to make sure that we wedge in something that has the correct constant with it. So we're going to wedge in RC, and now we can replace all the C's with X's as our variables here in line 8 with our existential in rule. So the crucial step here is that when we wedge in, we have to make sure that we select a term that has a constant that matches the other constant in our other term. Go ahead and pause the video if you want to try this one out on your own. Okay, looking at what we have here, we've got a universal quantifier and existential quantifier attached to this statement here. Our conclusion has two existential quantifiers, which might be a little worrying, except for now we have the existential in rule. So the nice thing is that we just need something that is Q and P with the same constants in these two different predicate positions, and then we can just add in our existential quantifiers later. That is convenient. The first thing we need to do then is just focus on our quantifiers in the first assumption. So first quantifier is the universal quantifier, so we have to get that out first using our universal out rule, and I'm just going to pick A for the different places for X. So again, be careful. X is the first, or is in the first position of this two-place predicate for P, and then it's in the second position of this Q predicate over here. So we want to make sure that we put the A's in those two positions, or in the correct positions, I guess I should say. And then we can get the Y out here in line 2. The only thing is this is the existential quantifier, so we have to pick something different. So I'm going to replace the Y variables with the B constants. And then now we have this statement here without any quantifiers. Looking at what we need up here, we need something that's Q blank blank and then P blank blank. The nice thing is that looks like this is going to work out in our favor. We just need to rearrange the conjuncts. So we're going to break them apart here in lines 4 and 5, and then we're going to reassemble them so that they're in the correct order, where Q is the left conjunct and P is the right conjunct. And then we just need to make sure that we attach the existential quantifiers in the correct order with the variables in the correct position. So the first one, we need to do the Y first because it's the nearest to our statement here. And where do we want the Y's to go? Well, the Y needs to go in the second position of this Q and the first position of the P. And look, that's actually going to work out in our favor because the B's, the A's are in the second position of the Q and the first position of the Y. So it's a little confusing, but we're going to replace the A's before we replace the B's here because they're in the correct position of the conclusion that we have up here. So we're going to replace the A with a Y, the A with a Y, and then we're going to replace the B's with an X here in the next line. So all the B's become X's, and so we get what we need to have here in the conclusion. Now let's move on to our quantifier exchange rule. So if we look at what we have here in this first problem, we've got an assumption with a tilde out in front. That means that the only thing that we're going to be able to do with this assumption is build a contradiction with it. But that's going to be really hard to do because we would need to build a universally quantified statement of px or qx, and there is no universal quantifier in rule. So actually that's not going to be helpful to us unless we can find a way to change this statement so that the tilde is not the main operator. Looking at the conclusion, though, again, tilde is the main operator, so we need to assume the opposite of that and try to build a contradiction. So line 2 should be ax px, and we're going to try to build a contradiction. What do we do here in line 3? We can't really do anything with this statement until we change the position of the tilde. We could get this out, but actually that's going to be counterproductive, as I'll show you here in a second. What we can do in line 3 is we can actually use our quantifier exchange rule, and what it does is it moves the tilde in to the inside of the quantifier here. So this tilde is going to get moved from the outside as the main operator to the inside of the quantifier, and then we're going to change or exchange or switch the quantifier from a universal one to an existential one. Now the reason why this works is, if you remember from the previous lecture where we talked about how tildes and quantifiers work with these statements, right? To say that it is not the case that all things are something, that's the same as saying that there exists something that is not whatever that statement was connected. So this is saying it's not the case that all things are P or Q. Here, this is just saying there exists something that is not P or Q. And those are equivalent. The same thing will be true when we use the quantifier exchange rule, where we have a tilde EX, and then we can change it to a universal AX tilde, again saying that if it's not the case that there exists something that's blank, and that's also saying that all things are not blank. So if you're trying to understand the meaning behind the rule, go back to that video to try to understand why we can exchange these quantifiers and move the tilde in and out, because they're equivalent. If you're just interested in understanding how the rule works, just think of it as I move the tilde across, it changes the quantifier. That's it. So now, based on what I have and why I said it would be counterproductive to get the universal quantifier out in 2, is because now I have an existential quantifier in 3, and I have to do existential quantifiers before I can do universal quantifiers. So I'm just going to pick the letter A as a constant to fill in the variables for these x's here, and now I can get this universal quantifier out to match what I have here. So that's what I'm going to do. I'm going to pick an A for this universal out rule, and then I'm trying to build a contradiction. Here is something that has a negation in front of it. Can I get the same thing but without a negation? Sure I can. I've got one of the disjuncts here. I just need to wedge in the other one. Once I've done that, now I have something that looks the exact same, just one of them has a tilde in front, so I can build my contradiction in 7 from 4 and 6, and then now I've got a contradiction, depends upon my PA in 2, so I can add a tilde to my PA 2 and 7 tilde in, and then I just remove the assumption number associated with the PA here in line 8. Instead of telling you to pause this video, I'm just going to go ahead and jump into it. I mean, if you want to try to pause the video real quick and try it for yourself, totally do it. But this one's going to be a little bit different because the quantifier exchanges could be working in the opposite direction as before. So if we look at what we have here, we have a biconditional statement as our first assumption, and we have a conjunction in our second one. So we're trying to derive R, and if we look at our assumptions, well, R appears in this biconditional So really all we need to do is we need to take this biconditional, change it into a conditional statement, and somehow get the antecedent of this conditional statement, and then we can get the R out. So that's pretty much all we can do with this at the moment. So let's focus in on our second assumption here. I'm going to separate out the tilde PC from line 2 using our AND out rule. And then I'm going to introduce an existential quantifier. So since I have something that's tilde PC, I can put an existential quantifier out in front of it, replace the C with an X variable, and now I can use quantifier exchange to move this tilde across. So I'm taking this tilde, which is on the inside, I'm moving it to the outside. And as I'm flipping it, I'm changing the quantifier from an existential quantifier to a universal quantifier. So flipping the tilde across from inside to outside, changing the quantifier from an existential to a universal. Quantifier exchange rule. So it works in both directions here. Then I can do the same thing with the tilde QB. I can get the existential quantifier in to make EX tilde QX, and then I can use the quantifier exchange to move the tilde across. So from the inside to the outside, existential quantifier to universal quantifier using the quantifier exchange rule. Now I have both of my conjuncts that are my antecedent here. So I just need to piece these two together. I need to piece 6 and 9 together to create the antecedent that is up in 3. Once I've done that, then I can get the R out. So 3 and 10, arrow out. Now I've got the R, and so that's all I need to do. But the reason why this one's a little bit tricky is we haven't really done an existential in where there's a tilde in front of the term. So that's different. And then also doing the quantifier exchange rule in the opposite direction. So going from the inside to the outside, that's a little bit different. But the whole idea is that those statements are equivalent. And so the quantifier exchange rule works in both directions. So I'm going to go ahead and jump in on this one because it's a little bit difficult, especially at the beginning, unless you have some pretty solid logic intuitions here. So if we look at what we have two universal quantified statements. That's pretty good because that means they aren't restricted. I can get them to match pretty simply. But if I look at my conclusion, it's a universal statement. And the thing about universal statements in the conclusion is that you can't build a universal statement because you can't just use a universal quantifier in rule. There is no such thing. You can only say that something exists. You can't say everything is based on a couple of examples. That's the reason why you can't have a universal quantifier in rule. So with that being said, what we have to do here is we have to assume the opposite of our conclusion and try to build a contradiction. So we're going to use our tilde out rule at the very end. Now what can I do? Well, I want to do the quantifier exchange rule on line 3 first because I know that it's going to change this universal into an existential quantifier, and existential quantifiers are limited. They are restricted in what I can write for them. So I'm going to use my quantifier exchange rule on 3 to move the tilde in inside the quantifier and then switch the quantifier across. So that's what I'm doing here. Taking the quantifier, moving it inside, so it goes from outside to inside. Universal quantifier goes to existential quantifier. Now I have 2 universal quantified statements and 1 existential one. So I want to do the existential first. That's what I'm going to do here in line 5. I'm going to replace the x variables with a constants. And now I have a tilde conditional, which also doesn't look very helpful, but remember that we're trying to build a contradiction, so this could be one side of my contradiction. So let's go ahead and get these other universal quantifiers out. So I'm going to get rid of this universal quantifier 1. I'm going to replace it with a's there. And then here in line 7, I'm going to do the same thing with my other universal quantifier. I'm going to get it out. So as I was just mentioning, I can use this as my contradiction, but I'm going to have to build PA arrow RA. And if that's the case, then I need to make an assumption of PA because it's the left side of this arrow, and I need to try to get to RA. So that's what I'm going to do. I'm going to assume PA as a PA. Again, sorry about the confusion if it's causing any. I just like to use A's as my first concept because I think it makes sense. So I made a PA. I need to get to the consequent of this conditional statement. So I'm going to put PA and QA together in line 9. And then I can get RA from 6 and 9. And now I made a PA of the antecedent. I got to the consequent here in line 10. So I can build my arrow statement in line 11. So PA is my antecedent, RA is my consequent, so 8 and 10, arrow in. Want to make sure that I drop out the assumption number associated with the PA, which is an 8, and then I can build my contradiction. I've got the same thing in line 5 and 11, just in 5 it has a tilde, so we'll put those two together. And then now that I got a contradiction, depends upon my PA in 3, I can remove the tilde that's associated with that PA in 3 with 3 and 12 tilde out, and then I just want to make sure that I remove the assumption number associated with that PA. So yes, quite complicated, but again, just trying to find the different steps that we have to do and doing them one at a time. Okay, looking at this one, I'll give you a chance to pause the video and try it on your own if you want. Okay, looking at what we've got here, we've got a universal quantified statement here and one assumption. We've got a tilde EXPX. Hopefully you can already see that we're going to use our quantifier exchange rule on this. And then we've got an existential quantified QX here. Looking at our conclusion, EXRX, if I can just get something that's an R, then I can use my existential N rule to build that. So right now it's looking like we don't need a PA because I've got an RX right there. I just need to somehow get something out that is an R and then add an existential to it. So that's the reasoning that I'm sort of employing here. So let's just go ahead and work with what we've got. So I'm going to immediately do the existential out rule for number 3, or line 3, I guess I should say, because I know I want to make sure that I do that first before I get any other constants on the board, and then I'm going to have to repeat some steps. So just best to get the existential quantifier out first. The next thing I'm going to do is I'm going to get the universal quantified statement out here, just to match that QA there. And then I'm going to use my quantifier exchange rule here on line 2. So I'm going to take this tilde, move it inside, take this existential quantifier, turn it into a universal quantifier with my quantifier exchange rule. So the nice thing here is I've got a universal quantified statement now, so I can just put in any letter that I want. I'm going to choose A to make it match everything else that I have here. And so what do I have? I've got a tilde PA, I've got a QA, I've got a conditional statement where those two are conjunction as the antecedent here. So that looks like we're in pretty good shape. We just need to build this antecedent. So in line 8, I'm just going to put tilde PA and QA together to build my antecedent, which is in 5. And then I can get the RA out from 5 and 8. Arrow out here in line 9. Now I've got RA. All I have to do is introduce an existential quantifier. So I'm going to replace the A with an X and put existential quantifier out in front of that R. And then we're all done. Okay, if you want to pause the video and try this one out on your own, totally go for it. But it is a little complicated. It does something that we haven't seen before. But I'm going to give you a chance to pause the video, try it for yourself if you want to. Okay, look at what we've got here. We've got two universal quantified statements. That's good because then we can get anything out for those universal quantifiers that we want. But the conclusion is a universal quantified statement as well. So that means we're going to have to assume the opposite and try to build a contradiction. Now, there are a couple things that we could do with 3 because we have tildes on the outside of the quantifier and on the inside. We could actually move this tilde to the outside and have tilde tilde ex px, but we're not going to do that. Instead, we're going to move the tilde inside with our quantifier exchange rule and create something that looks like this, ex tilde tilde px. Then, since we have an existential quantified statement, we want to make sure we get that out first, so we're going to make tilde tilde pa. And then this is where it gets tricky, that you might not have thought about this, because once I use my quantifier, or my universal quantifier outs on these, I'm going to have PAs, not tilde tilde PA. So I need to somehow show that tilde tilde PA is the same exact thing as PA. Again, I don't think we've talked about this before, but saying that not PA is the same as saying PA. But we have to prove it. So we're going to assume tilde PA as a PA. This is where things start to sound a little crazy, but tilde PA and tilde tilde PA are contradictory, so we can build a contradiction here in 7, and then we can subtract the tilde from this PA here by doing tilde out. And now we've got PA by itself instead of tilde tilde PA. So that's a lot of work there to get rid of the double negation. There are actually shortcuts for that in logic. There is a derived rule for double negation that means that we don't have to do any of this, but haven't showed you that, and just want to also show you that we can get to what we have to by just using our rules in the same way that we have been. So now that we've got PA, this is pretty simple. We just need to use our universal quantifier out rules to get the individual conditional statements, because then we can put the PA in for our conditional statements here to get the consequence. So got a conditional statement, put the PA in, get the QA out, and then we just have to repeat for 2, use the universal quantifier out, and then we can get the tilde QA from that conditional statement. And so now we've got QA and also tilde QA from 10 and 12, so we can ampersand in there. And now I've got a contradiction, depends upon my PA in 3, so I can get rid of the tilde that I had in there. And then just got to make sure that I drop out the PA number here in the far left. We're going to look at a couple of examples with two-place predicates in the quantifier exchange rule. So the quantifier exchange rule works the exact same for two-place predicates, but it does get a little bit more complicated when you have to go across multiple quantifiers, just because you have to make sure you do each step one at a time. So if we look at this first example here, we have a tilde that's out front of these two existential quantifiers. So we're going to distribute, or not distribute, we're going to move the tilde across each of these quantifiers one at a time. So based on what I have here in line 1, I can move the tilde across from the EX in front of the EY. So I know this probably looks a little odd, but we have to move the tilde one quantifier at a time. So we're taking it from the outside of the EX, and then we're going to move it to the inside of the EX, but outside of the EY. And then we're going to switch our quantifiers around. Now, what's the main operator here in 2? It's not the tilde. We can't do quantifier exchange because the tilde is not the main operator here. And instead, what we're going to do is we're going to have to do our universal quantifier out rule. So we're going to use our universal quantifier out rule to put in an A for our x variables here. So now we've got tilde EY PAY. And so now our main operator is the tilde again. So what can we do? Well, we can do the quantifier exchange rule to move the tilde inside again and flip the existential quantifier into a universal quantifier. Now that we have a universal quantifier, we can do the same thing as before. Since we're looking for PAB, we're going to replace the y's with a b, and now we got tilde PAB. So the difficult thing here, I guess, is knowing that we can only move the tilde one spot at a time. We can't then move the quantifier, or we can't move the tilde again on the inside here. We have to treat this as the main operator. And so we got to get the universal quantifier out, and then we have the tilde again as the outside, and then we can move it again with the quantifier exchange. So this practice problem is pretty tough, but I think it's instructive, which is why I chose it. So instead of telling you to pause the video, I'm just going to go ahead and go through it. If you want to try to pause the video and try it, go for it, but I'm just going to go ahead and hop into it anyway. So what we have here, if we look at our argument, we have existentially quantified statement, so that's restricted in certain ways, and then we've got this biconditional statement here, and if we look at our conclusion, it's a wedge statement, and we're going to end up building it with tilde q because I don't see an r in any of these assumptions. So we need to get to tilde q, and it's pretty obvious what we need to do. Then we need to get the biconditional out, and then we need to get the antecedent, and then we can derive tilde q. But before we get there, we need to somehow get tilde ax, ay, pxy. And we're going to be able to get that from 1, but it's going to take a lot of work. So first thing we can do, existential quantifier, that's our main operator here on the outside, so we can do tilde, we can do ey tilde pay with our existential out rule. Next thing we want to do is we actually want to do our quantifier exchange rule. We want to move this tilde across to get tilde ay pay. So we're going to use our quantifier exchange rule to move this tilde to the outside and flip the existential quantifier. The next thing we want to do is we actually want to reintroduce the existential quantifier. We're going to replace the a that we just put in there with an existential quantifier in that first place. So now we got ex tilde ay pxy. And since we have a tilde on the right side of that existential quantifier, we can move it across again. So it's a lot of work to build this tilde ax, ay, pxy. But that's how we can move this tilde across from the pxy here all the way to the other side. Now that we've got that, it's pretty straightforward. We just get the double arrow out from 2. And now we've got a conditional statement. We've got the left side of that conditional statement, so we can get tilde q here in line 8 from 6 and 7 arrow out, and then we got tilde q, so we just have to wedge in the r, and that's it. So this is really complicated because you have all these different steps from 3 to 6 to build the antecedent for that conditional statement, but hopefully you can see how the different rules are getting applied in each case. So this one is a challenge, to say the least. But if you want to try it on your own, go ahead and pause the video. So if we look at what we've got here, the reason why this one's a little bit scary, and also it's going to get complicated because of what we got to do with the conclusion here. But you see you got one universal quantifier on the outside, and then you got another one on the inside. The reason why this one's on the outside is because you got a one-place predicate here, and then you add in the other one here because it's only operating over this statement. So you got a qy that matches that universal quantifier, and then you have the universal quantifier also right there. You got the y variable for both of those. So that's why it looks the way that it does. Looking at the conclusion, it's a universally quantified statement, so we have to assume the opposite and try to build a contradiction. Since we have a tilde out in front of a universal quantifier, probably best to go ahead and do our quantifier exchange rule to get this. And so, got an existential quantifier, I should go ahead and get that out because it's restricted, so I'll use A's in all the positions. And so now I've got tilde and then this conditional statement. And since I'm looking for a contradiction, I'm going to need this somehow. The only way that this is going to be meaningful is if I build a contradiction where the other side of the contradiction is QA and PA arrow RAA. So how do I build this arrow? I have to assume the antecedent and try to derive the consequent. So that's what we're going to do here in 5. And that's why it gets pretty tricky. We're going to break this down into its two conjuncts in 6 and 7. And then we can go back up to our universal quantified statement. We can put in anything that we want for x, so we're going to put in a. So just be careful again. We want to make sure that we put the a in the correct spots. So the x is attached to the p here, and that's in the first position of this r up here. So that's why a goes here and a goes here. I still have these y's, which I can't do anything with yet because the main operator now is this conditional statement. Or sorry, this arrow. So I can get the consequent though from 7 and 8 arrow out, and now I have a universally quantified statement in 9. And since we're trying to get something that is RAA, we should use another A for our universal out again. So now we get QA arrow RAA. And if we look back at 6, I've got the antecedent for this. So I can get RAA out from 6 and 10. And now we assume this QA and PA to get to RAA. That's what we got to here in 11. So we can build the arrow that we were looking for here from 5 and 11, arrow in, drop out the 5 associated with our PA. Now we can build our contradiction. It looks very complex and monstrous, but it's really just here's the one that we just built, and then here's the one in which we got from doing our quantifier exchange and then our existential out rule. So those two match. Their contradiction depends upon the PA in 2, because that's where we're getting the other part of our contradiction from. So we can tilde out on our PA in 2 with 2 and 13 tilde out, and then we just remove the assumption number there. We will not get that complicated for most of the problems that we do in the class, but I just thought it would be a fun one to show you how far we've sort of come in our journey in logic, and how something like this would have probably scared you at the very beginning, and now we're at a much better position. You'd see each of the steps play themselves out.